Hello, welcome back to our organic chemistry lecture series as we're working on our carboxylic acid derivatives. Today we'll be talking about a new carboxylic acid derivative we haven't seen before, a brand new functional group for us. Where we're going to have a carbonyl attached to an oxygen. This oxygen then attached to another carbonyl. So we have two carbonyls directly attached to one oxygen. This is going to be our acid anhydride. Now, the interesting thing about this is that we talk about the reactivity of this functional group here. We'll see that it has the same reactivity of our acid chlorides, okay? Very similar activity, which tells us what? It's going to tell us that this group here is actually going to be a fairly good leaving group. And we'll talk about that as we do some mechanisms. So since it has a similar reactivity than of our acid chlorides, it can do all the same reactions. Now, we're not going to go through the mechanism every single one, but we'll go through a couple of them and just to show you the example of that. Okay. Well, first we'll start with how do we make an acid anhydride? How do we make this? Well, they're going to come from our acid chloride reacting with our carboxylate anion. Okay. And as you can guess here, this is going to work as our nucleophile. It's going to attack our carbon to carbonyl. Right? Very similar to what we saw before. Remember, this acid chloride is very reactive. Not a problem. And we get to this step here. And just like we saw before, what's going to happen next? Electrons are going to come down, and we're going to kick off our chloride. To generate our acid anhydride. Okay? So this is how we can make it. It comes from a acid chloride reacting carboxylate anion, right? Through this type of mechanism. Now, the next thing we'll talk about a little bit is that we talked about the reactivity of this one being very similar to our acid chloride. We find out here that actually this group here is going to be a good leaving group. Okay? It's actually a very good leaving group. And as we do a couple mechanisms, we can go through why is that a good leaving group. Like I said, we're not going to do every mechanism. We'll show every reaction. We won't do every mechanism because they all follow the same trend, the same pattern we saw for acid chloride. Okay? So let's start with a couple. We'll do a couple mechanisms, and then go through reactions for our acid anhydride. Okay? So let's do that now. All right, so I'm going to take my acid anhydride and react it with our alcohol. I already guessed kind of what's going to happen. Follow the same trend we saw for acid chlorides. We're going to see what? We're going to see attack there. Electrons go up. And we get to this form here, right? As we saw before, electrons are going to come back down. Oops, electrons are going to come back down. And what? We're actually going to kick off this group here. And we get this species here. And then so we're at this point here, right? Where we kicked off our leaving group here with this carboxylate anion. And so really, before we finish this mechanism, let's look at this group here as our leaving group, right? This was our leaving group. So briefly, let's look at that leaving group here. I'll run it over. Now, if we look at this in terms of being a leaving group, why is it a good leaving group? What are the characteristics of our leaving groups? Remember, characteristics of our leaving groups are things that, when they came off, they're very stable, right? They're very stable. They're not very reactive. So we have to look at this in terms of what's the reactivity of this? How reactive is this carboxylate anion, right? Is there any way to stabilize that negative charge? Can we stabilize the negative charge. All right? Is there a way we can stabilize that negative charge on that oxygen? If we can stabilize the negative charge, that's how we can prove that that's a good leaving group, because that charge is going to be stabilized. What do you think we can do to stabilize that negative charge? How can we stabilize it? Is there a way? Is there a way maybe this oxygen doesn't have all that electron density, right? Maybe it can share with that oxygen. What can we do? We all know what we're thinking, right? We're all thinking the same thing. We're thinking we can do what? Electrons go here, electrons go there. What am I doing? I'm drawing what? Drawing a resonance structure. Right? And so by doing that, is what do? We've moved the electrons. They're on this oxygen. Now the electrons are more on this oxygen, right? We have delocalization of that negative charge over two atoms, right? Can we stabilize the negative charge? Yes, we can. Yes. We can stabilize the negative charge. You stabilize negative charge by resonance. Right? That negative charge here can be stabilized by resonance as its electrons are moving back and forth. Half the time it's on this oxygen, half the time it's on this oxygen. This helps stabilizing that negative charge, which overall means what? This is a good leaving group. Right? So it tells us that this carboxylic ion is actually a pretty good leaving group because that negative charge is stabilized over two atoms, right? It's just kind of hanging out on this oxygen a little bit, hanging out on this oxygen, right? And so it's being stabilized, meaning that it's not very reactive, right? It's okay having that negative charge there because it's being stabilized by resonance, okay, resonance, right? So meaning that this is going to be our leaving group, it's actually going to be a pretty good leaving group, right? It's fairly comparable to our acid chloride, right? On the same level as our acid chloride, right? Not as good a leaving group as chlorine, but very close to that chlorine, okay? So we can stabilize the negative charge. So back to our mechanism here, our reaction. So this is a good leaving group, comes off. We got one step left. Now, not only is this going to come off, but it's going to be what? It's weakly basic. So we can use that to then what? Deprotonate. So not only is it serving as a leaving group, it's going to serve as our base as well. Oops. Oh. This would be one. Plus, what do we generate? We generate this acid as well, right? So the carboxylate, so in our acid anhydrides, as we do these reactions, we're going to kick off our leaving group here. This also can serve as a base too to help deprotonate things if we need to deprotonate something, right? But at the end result, we get what? We get our ester out. Okay? So we can take our alcohol, react it with our acid anhydride to generate our ester group. Okay? And we can see this by talking about this. So we can see this carboxylate ion that comes off is actually going to be a good leaving group because that negative charge is going to be stabilized, right? Just how our chlorine is a good leaving group because that negative charge of the chlorine is stabilized, right, by some other effects. Okay, so we help stabilize this. So we can see that this acid anhydride is going to do lots of different reactions, right? It's going to be very reactive. We saw for just like our acid chloride. So let's look at a couple more. So we did it with what? With our alcohol. And let's look at a different reaction that we can do that shows the reactivity. How about with our green group? R. So what happens if I react it with a green group? Call this R1. MdBr. Again, as before, we have these water second step. This will be excess. Right? These reactions are always usually in excess, right? So what do you think we're going to get in this? And you can guess what we're going to get, right? R, R1, OH, R1, OH, right? Not surprising, what are we going to get? We're going to get a dish of two groups, right? two groups to our acid anhydride to make this tertiary alcohol. We'll go through the mechanism of this one. But again, very similar mechanism that we saw before, right? Just for fun, because we always like doing mechanisms. We do these all day. And now I have a lot of time to do a lot of it. Right? So this is going to attack here. Again, in this case here, it doesn't matter what carbon we attack. If it's symmetrical, acid anhydride, doesn't really matter. We can attack either side. When it's not symmetrical, it gets a little more tricky, a little bit messier, right? But for now, we'll say our symmetrical acid anhydride. Again, as we get to this form here, electron's going to come back down from a carbonyl, and we're going to kick that group off, right? We're going to kick off that carboxylate, because we talked about already, that being a very good lead. Kick it off. And we get there. Look at that. By kicking this group off here, we're going to kick it off and not have to worry about it. We make that what? Ketone. We make a ketone. Again, ketones are very reactive to our grignard. That's why our grignard is in solution. We have more of it. One there. Okay, so I've got our second addition of our groups, and then we're going to do what? What's going to be our last step? Water. Got to put that water in there to neutralize everything, right? Got to neutralize. Okay, and so from that, what we get addition of our second R group here to make this tertiary alcohol here. Again, we took our acid anhydride, reacted with our first grignard reagent. We kicked off our lead group to generate what? Generate our ketone. This ketone then is reacted again with our grignard reagent to form our final compound, which is going to be what? It's going to be our tertiary alcohol. So this is with our grignard reagent. Okay? Very similar that we saw with our acid chloride. Again, very similar mechanism, right? And so what we can see here is it follows the same trend we see for acid chlorides in terms of very similar to the reactivity, and the mechanisms are identical. And so briefly, what we can do then is just list those reactions that we can do. Again, all the mechanisms are very similar to our acid chlorides, right? So I can take this, and I can react it with R1OH, R1. We got a little bit of technical difficulties with my. And we're back. Oh, it's wonderful. It's going to go up. We can do that reaction. I can react it with just water. We can get to here, right? I can take my anhydride and do what? We do a grignard. Excess. First step. Second step is going to be water. And what do we do? OH, R1, R1. Again, this could be different alkyl groups, right? Any type of alkyl groups. Doesn't matter. Just showing that we had two of them here, and we had one that we started with from our acid anhydride group, right? So we do these type of reactions. I can take this and react it with what? Lithium anhydride is an excess, right? 2 with water, and where are we going to get? You can guess it. Just like we saw with our acid chloride, OH. We're going to add 2 groups here, right? 2 groups. So you can see with our anhydride, we do all those similar reactions to all the acid chloride. Which reaction am I missing? What's left? One more. Missing my amines, right? RNH2. Again, excess. Excess with my amine. It gives me what? It makes my NH2. And again, I can do, it could be NH2, or I can have other R groups there as well, right? Actually, this one is RH2. I'm sorry, this is going to be NH with R here, right? And I can have two R groups there, or I can have no R groups there, right? And you get different substitution patterns based on that for the amine. So we see for our acid anhydride, we can do all those same reactions solve for acid chloride. All the mechanisms are identical to our acid chloride mechanism. Okay, all similar ones there. So keep that in mind. And that gives us our overview of our acetic anhydride. Okay, and what we can do with it, our acid anhydride. All right. So this will be for these mechanisms. Feel free again. What's important here is that we know what we understand how they work, and all the mechanisms are very similar to each other, right? Very similar to the acid chloride mechanisms. Okay. And just understand reactive products. Our acid anhydride with water, I can make a carboxylic acid. Okay. All similar, right? Thanks.